Okay, so this is chapter 16, section 16.1. This is the last chapter that we will do in all of calculus. So let's get it started. 16.1, this is going to be relatively short compared to the rest of the sections in this chapter, which are definitely not short. This one is vector fields, and it's kind of an extension of slope fields that we saw in Calc 1 and 2. So we're going to extend this to the idea of vectors now. So our outcomes, we're going to be able to take a look at the idea of a vector field, the position vector, perpendicular vector fields, unit vector fields, and the gradient vector field. So we're going to take a look at all those different things. Really a very simple overall concept. So the idea is we're going to consider the vector valued function here, f of xy equals the vector 3 comma x. So if we want to sketch what the vector field might look like, and we're not going to do this for every possible place, every possible point that we could do, because that's going to take way too long. We're just going to do it for a select few. So I'm going to create a little chart where the left-hand side is going to be my point, and the right-hand side is going to be my vector, f of xy. So if I start at the point 0, 0, then the vector itself, by definition, is going to be the vector 3, comma, whatever the x value at that point was, which was 0. Same idea, if I keep going, I'm going to take another point like 1, 1. So my vector then is going to be 3, comma, 1, because it's 3 and then the x value. So if I take the point 0, 1, well, then the vector is 3, comma, 0, and so on. I'll just do a couple more just so we have an idea. So like negative 1, 1 would be 3, comma, negative 1, and then maybe like negative 1, 0 is also going to be 3, comma, negative 1. So again, it's just 3, comma, whatever the x value at that point is. So if I was to sketch this vector field, well, let's see. I'm going to go out, let's see, 1, 2, 3 units in every direction, just to give it some kind of a scale here. So my first vector is going to be created from the point 0, 0, and it's going to be the vector 3, 0. So from 0, 0, it's going to go right 3 and stop. That's my first vector. From the point 1, 1, the vector is 3, comma, 1. So from the point 1, 1, the vector is right 3. I guess I should have gone out a little bit further. Right 3 units and then up 1 unit. It's going to be more like ending right there. So it's going to look something like that. And then from the point 0, 1, which is going to start right here, it's going to go out 3 units to the right and then stop. So it's actually going to be parallel to the first one that we did. And then let's see if we started the point negative 1, 1. Negative 1, 1, it's going to be up here. That's going to be the vector 3, negative 1. So it's going to go right 3 units, 1, 2, 3, and then down 1. So it's going to finish there. It's going to look something like that. It's going to be really hard to tell what this vector field specifically looks like, but this is the general idea of how we would find them. We start at the point negative 1, 0, which is right there. It's also the vector 3, negative 1. So we go right 3 and then down 1. It'll finish there. Oh, that was horrible. Wow, I just cannot seem to draw a straight line in that direction. I'm going to go backwards. Slightly better. So, and then you would just keep doing this for every possible point that you would want to create one of these at. So if I wanted to do the full 3 by 3 section, and I'd have to do all the different values, you would figure out what the vector would be, and you would draw what the vector looks like. And that would create an entire field of vectors. So that's how you would draw a vector valued functions vector field. Okay, really not much to it. So the question might be, well, okay, that's easy enough to do. Why would I want to? I mean, what's going on with it? what are some of the uses? Well, we'll talk about that after we do this particular vector field here. So this one, now we're in 3 dimensions. So it's f of x, y, z equals k. Remember that k is basically your z component, and the coefficient of that is 1. That's basically like f of x, y, z equals 1k. So that means, and yeah, so let's write that down. So k is the vector 0, 0, 1, right? Because it is the unit vector in the z direction. So what that's saying is the vector field is always going to be that unit vector. So no matter where it is on my graph, if I were just to sketch a 3-dimensional space here, I don't care what point we're at, it's going to be 1 unit in the vertical direction. So if I start at the origin, it'll go up 1 unit. If I start at, the point, I don't know, 2 on the y-axis or something like that, it'll go 1 in the vertical direction. Or if I go to like 7 on the x-axis, it'll go 1 in the vertical direction. Anywhere that I want to put a vector in this entire vector space is going to be 1 unit in the vertical direction. Not really that difficult. It'd be kind of interesting to see the entire field of that, because all it would look like is one big solid, almost look like a bed of nails or something. I don't know. It's going to look like a whole bunch of vectors just stacked upon themselves. But you get the idea that every vector would be pointing straight up. So what are some of the uses? Like, what are vector fields good for? We know that when we did slope fields, I mean, we could project those into things like weather reports. If you're talking about how the what do they call it? The jet stream comes from Canada down into the United States and then makes the weather pattern do a certain thing. It kind of follows some kind of a slope field. This is the same idea. We're going to do this, but now it's 3-dimensional. So some of the uses, and one of the main uses that we're going to talk about, is fluid flow. How fluids flow through like a river or through some kind of like objects or things like that. One of the other things that we're going to talk about are force fields. Not like force fields that you would have, in science fiction movies, but the idea behind them is actually the same thing, but we're probably going to use them more as magnetic fields. So fields that are created by some kind of a force. And in our case, again, we'll probably primarily use magnetic fields. And then things as simple as wind. Okay, wind fields are also going to be used in there. Wind can be defined as, not defined, but can be shown using vector fields. So those are some of our uses. And then we're also going to be able to take this way into the future when we talk about flux. And I know some of you have taken Physics C or are taking Physics C, and you've already dealt with flux. So we're going to be able to use vector fields to also describe stuff with flux, but that's not going to be until much later in the chapter. All right, so let's go ahead and move to the position vector. So we want to consider the position vector field for x, y. Okay, again, not really that difficult to do any of these things, and I really don't expect that you're going to have a hard time with any of this stuff. So if you want to do the position vector, again, the position vector is always going to be defined as x, y. So whatever your point is, 0.1, 1. Well, that's the vector 1, 1. The point, geez, I don't know, try something completely different. 5, negative 2. That's supposed to be a negative 2. Would be the vector 5, negative 2. I'm not going to do a whole heck of a lot of those, but you get the general idea. So if we were to sketch this, and I were to start at the point 1, 1, which is about right here, it's going to be the vector, right 1, up 1. It'll look just like that. And then if we were to go to the point 5, negative 2, so that'll be way out here somewhere, right about there maybe, to start, then we're going to go right 5 units and then down 2 units. So it might look something like this, 5, negative 2. and that's what's called the position vector field. Basically, it says that your vector is going to be exactly the same thing as the starting position as far as the terms are concerned. So you go to that starting position, draw the vector based upon that. Again, not really difficult to do. The perpendicular vector field. Okay, I kind of hesitate to do this one completely, and hopefully you'll understand why. But it is important to know what the perpendicular vector field is. So again, we'll create a little bit of a chart. This is actually not one I'm going to completely finish. But the perpendicular vector field is negative y, x. So if you think about what we just did there, I took the point, which is xy, and I flipped the x and y and made it negative, or did the opposite reciprocal in order to get basically what would be perpendiculars. Hopefully that makes some sense. So if we start at 1, 1, the vector is, well, it's now the negative of y, which is negative 1, and then x, which is positive 1. If we did negative 1, 1 for our starting point, it's negative of y, so that's negative 1 times the, not times, then the x value, which is also negative 1. And then if we do negative 1, negative 1, the negative of the y value is positive 1, then the x value is negative 1. And then if we did, 1, negative 1, and let's see, the negative of y, which is 1, and then the x value, which is 1. And then if we did like the point 1, 0, the negative of 0 is still 0, and then the x value is 1. So if we sketch this, so let's see, let's start at the point 1, 1. We start at the point 1, 1, which is about right here. The vector itself is negative 1, positive 1. So we go backwards 1 and then up 1 on the x-axis. So it looks something like that. Okay, but if I were to start at the origin, and this is why they call it the perpendicular vector field. If I was to start at the origin and I was to draw the vector, the position vector, that would have just been this particular vector. And now you can see how that would be perpendicular. And I'll show you one more like that, and then I'm going to stop with that one. So let's do from the point negative 1, positive 1. So the starting point would be about right here. According to this, that vector is negative 1, negative 1. So it's going to go down 1 and left 1. So it's going to finish right about there. Once again, however, if we were to take the xy and do the position vector based upon this, that would be negative 1, positive 1. It would actually meet right there. So I'm not going to finish this one. If you actually do finish drawing all the perpendiculars and its positions, you'll understand why I'm not going to finish this one, because it looks too much like a symbol, which is not very good, actually. So I'm going to stop right there. But you get the idea of the position vector, excuse me, the perpendicular vector being perpendicular to the position vectors. Okay, a unit vector is exactly what it says. It is a vector that is a unit vector. So, excuse me, unit vector fields. All of them are going to have a length or a magnitude of 1. So if we simply start off with the position vector, which is xy, and I want to make that a unit vector, to make all the position vectors a unit vector, we divide by their magnitude. So the unit vector field would be x divided by the magnitude of xy, which is going to be each component squared, added together, take the square root. So it's divided by the square root of x squared plus y squared, and then y divided by the magnitude, which is square root of x squared plus y squared. So that would be your unit vector field. I'm not really going to sketch this one, but all vectors would have a length or magnitude of 1. So that's how you would create a unit vector field. All right, now we've only got one more to talk about. Probably the shortest lesson we'll do all year, which is the gradient vector field. And remember that the gradient of a function is going to be the partial derivatives. So let's see, if we take the derivative of this thing with respect to x, it's going to be 1 over 2x plus y times the derivative of that thing with respect to x, which is going to be 2. So we get 2 over 2x plus y, comma, and then the it's going to have the same denominator for the y part, because it's going to be 1 over 2x plus y times the derivative of the inside of the chain rule for the y part, which is going to be 1. And that is your gradient vector. And then you simply draw a bunch of vectors based upon points for that slope. Again, I am not going to draw those out. I think that this lesson is insanely easy for most people to understand, especially at this level of calculus. So I think that that's pretty much all we needed to do there. And that's plenty enough to get you guys started on the homework assignment. I think you should have plenty to be very successful with this. We will come back to this again. This will be used later on throughout the chapter as well, but that's good enough for now.